Now let's look at the domain of a logarithmic function. Basically, whatever is inside of a logarithmic function must be positive. Okay, you may not have the log of 0. It specifically needs to be positive. So in this case, x plus 7 must be greater than 0. Therefore, x must be greater than negative 7. And our domain will be from negative 7 to infinity. Now that we've seen how to handle the domain of a logarithm, let's go back and summarize everything we know about domains. If you have an x minus 2 in a denominator, we have to say x minus 2 cannot equal 0. Therefore, x cannot equal 2. And the domain in this situation is going to be all numbers except for 2, skipping over that one value. When you have a square root, you know that the radicand, x minus 2 again, must be greater than or equal to 0. So this time x must be greater than or equal to 2, and the domain is from 2, which we include, up to infinity. Now we're going to have the log of x minus 2, and x minus 2 must be greater than 0, meaning x must be greater than 2, and the domain will be from 2 to infinity. Now I put all three of these side by side specifically to highlight something. When you have a denominator, you're paying attention to it not equaling 0. When you have a radical with an even index, you're making sure that the radicand is set to be greater than or equal to 0. And when you have a logarithm, you're making sure that the argument is greater than 0. Hopefully seeing all three of these side by side helps you. Now let's begin to solve some basic logarithmic equations. We don't like this logarithmic form, so what we're going to do is change it to an exponential form using what I called the visual property earlier. This would be x to the 4th power is equal to 16. Well, you know that we need to set this equal to 0. So x to the 4th minus 16 is equal to 0. This factors into x squared plus 4 times x squared minus 4. Now we know that we're going to have plus or minus 2i as solutions coming out of that sum of squares, and we don't want to have imaginary bases because we're solving for bases. And then we're going to have plus or minus 2 as solutions coming out of the x squared minus 4. However, bases, just like the arguments, cannot be negative, so we're going to get rid of that plus or minus sign and only have 2 as the base in this case. For number 10, again, we're going to convert it from logarithmic to exponential form, and we're going to be able to say 3 to the 5th power is equal to x, and we can just multiply that out and find out that 243 will be our value of x. In problem number 11, we're going to say 5 to some power is equal to 25. So 5 to the x equals 25. Right now, we only know how to solve this by inspection, and we can guess that the solution is 2. If the numbers were not so clean, we'd have to apply a different method, which we'll be learning later in this chapter. Now we move on to evaluating logarithms. Well, this is actually rather easy. We're going to pretend there's an equals x on the right. And if we said 3 to the x equals 81, basically what we're going to do in our head is we're going to say 3 to the, I don't know, equals 81. And then we say, 3 to the 4th equals 81. Now we don't write that equals x there because that's creating an equation where there isn't one, but let's try it without again. I'm going to say 10 to the whatever equals 10,000. Well, there's 4 zeros in that 10,000, so again this will equal 4 also. In this final problem of this type, we're going to say base 2 to the makes 1/64. Now this one may stretch your head a little bit. It's going to have to be a negative value to bring this 2 to the power down to the denominator, so we know our answer will be negative, and it turns out that 2 to the 6th is 64. So negative 6 will be the value of that logarithm.